In this video, we're going to identify all the local max, all the local min, or all the saddle points for this surface. Okay, so locate the critical points. So the critical point, so something weird happens when fx equals 0, fy also equals 0. So so from here, take the partial derivative with respect to x. That will then give us this. Take the partial derivative with respect to y. That will then give us this. So now we demand that this thing equals 0 and this thing equals 0, because something strange happens when both of these equal 0 simultaneously. So now we're going to look at the domain, the xy domain, find out all the locations where both of these equal 0 simultaneously. So hang on, looking at this, you've got one block multiplying with this block. Whenever y equals 0, then the whole thing will be 0. So that means when y equals 0, y equals 1, y equals 2, y equals 0 is along here. So any time that you're on this line here, then you know you would satisfy this thing here. So anything on this line will satisfy this. And then if you look at this component, cos of x equals 0 at, well, this is 2 pi here. If you look at pi over 2, then anything on this vertical line will imply that this whole thing here would be 0, and this point here, 3 pi over 2. So anything on this vertical line here would also mean that this whole thing here is 0. So you can now see the pattern. Multiples of, well, if you jump, there will be more vertical lines over here, more vertical lines over here. Just know that you can keep on going to the right and keep on going to the left. So this thing here would be satisfied any time you're on this horizontal line or these vertical lines. Okay, so bear that in mind. And then now, hang on. So now looking at this this equation here, sine looks like this. So anytime it's at 2 pi, negative pi, and so on, basically multiples of pi here. So so hang on. So anything that's on this vertical line here, hang on, let me choose a different color. Let's choose blue. So anytime you're on this vertical line here, this vertical line here at negative pi, you know you will satisfy the second one. Okay, so hang on. You know you will satisfy the second one. Well, if you want to satisfy both of them at the same time, then you know that you must be on the horizontal line and the blue line. So basically we are talking about these points here, the blue lines and the so at these points here, and 0 as well. Hang on, let me think. Is it 0 as well? Let's look at this. Cos, yeah, and 0 as well. So so we know that n pi, comma, a height of 0. All these points here, we know that you will satisfy this condition where both of these equal 0. So we know something fishy is going on at these points here, but we don't know if it's a saddle, if it's a local max, a local min. We've got to do the second derivative test. So looking at the second derivative test, we now need to look at fxx. So hang on. So let's look at the concavity. So fx here, take the partial derivative with respect to x again. That will then give us this. and looking at this, take the partial derivative, because second derivative test we need fyy as well. So when you differentiate this with respect to y, it's going to be 0, because this whole thing here is a constant. Well, anyway, fxx equals this, and fyy equals 0. And then now if you evaluate this at all those points, it equals 0, because if you look at when you put y into here, it's going to be 0. So this thing here evaluated at this here is going to be 0. And then the second derivative test, we need to know fxy. We need to know fxy. Well, going back to here, we need to know fxy. Remember, fxy is the same as fyx. We've done this before. So both methods will lead you to the same answer. So looking at this, now we need to differentiate this with respect to y. So y is a variable, this is a constant. So when you differentiate it, it would just be cos x. Okay, so that's why fxy equals cos of x. Okay, so now hang on. So fxx evaluated at our point will always be 0. So the concavity is not concaving up, and it's not concaving down in the direction of xx. So now we need to look at this quantity here. So looking at this quantity, fxx equals 0. We need to look at fyy. Fyy also equals 0. And then now we need to look at fxy. Fxy equals this. So if you look at the course graph, it looks like this. Remember, this thing here jumps multiples of pi. So pi here is -1. 2 pi would be +1, -1, +1, -1, +1, negative. So you know that this thing here oscillates between -1 and 1, -1 and 1. Either case, you're going to square it. So that would then give you a +1, because you're squaring it. So this thing here will be 0. The whole thing would be 0, and then you take away. So it's going to be, this whole thing here would be 0, and then you take away, and then this thing here, I know it oscillates between -1, 1, -1, but when you square it, it's going to be 1. So 0 take away 1 would be -1. So this quantity here is actually -1. Well, -1 is not bigger than 0, so it's not going to be this scenario. This whole thing here turns out to be -1. Well, -1 is not bigger than 0, so it's not going to be this. It turns out that this thing here is -1. -1 is not the same as 0, so it's not this. It's not inconclusive. It's actually a saddle point. This thing here is a saddle point. So we can conclude that this thing here, well, this thing here is being less than 0, so we can conclude that these multiple points here turns out to be saddle points. Okay, so if you punch a surface into a 3D surface plotter, if you look at this point here, it's a saddle point, because and this point here is a saddle, this point here is a saddle, and so on. So if you drop a tennis ball here, it could roll down the hill. It could roll down the hill, or it's possible if you're here, you can climb uphill. You can climb uphill. So it is a saddle point right here. Okay, and also here, and so on.